All right, so we are live, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And of course, there are no classrooms right now. All of you are joining at home on YouTube, so we really appreciate you tuning in as we continue to highlight amazing scientists, explorers, and facilities from around the globe. Today, we are joined in Columbia in Maryland by a new speaker who's never joined us before on a topic that I'm personally very excited about. So Viranga Perera is joining us, and he is going to talk about the amazing story of the moon. He's a postdoctoral researcher. He's going to highlight how the moon formed, some of the other amazing bodies in our solar system, and some really cool tools you guys can use at home to check out a little bit more about the moon. So without further ado, thank you so much for joining us, Viranga, and take it away.
Thanks for having me. You can see the screen okay? Or?
Yeah, it looks great.
Good. So I'm going to talk a little bit about the moon, just give you an overview of some cool stuff about the moon. There's a link below or a website you can get to. It's quickmap.lroc.asu.edu. If you want to follow along, this is a really neat tool that Arizona State developed. And it's kind of like Google Maps for the moon. So before we talk about some science and the story of the moon, it's kind of cool to just take a look at it. So I'm gonna pause for a second, switch over to my...
While you're switching to, I just want to note, I just put that link in the chat bar for anyone tuning in on YouTube. So if you guys want to check that out too, while the presentation's going on, it's all there for you.
Cool. So this is what it looks like. And I'm sure most of you have seen the moon at some point, and when you look up at the sky. And I just want to point out some cool stuff that you might come across. So one thing I like to do with this tool is go up to the top left and click on that globe and switch to the lunar globe so that it's a 3D object. You can pick it up and turn it around. If you click here, it'll just minimize that menu. So here's the moon. That's the side of the moon you normally see from the Earth. There are these dark spots on the moon. They're individually called mare, or the plural is maria. And these are lava flows that happened a long time ago, billions of years ago. And one thing I'd like to point out is that some spot that you probably want to pay attention to when you look up at the moon next time is this spot right here. And that's where Apollo 11 landed, somewhere there. So one cool thing about this tool is you can point that out for yourself. If you go to these 3 bars here, they're layers. And if you click on overlays, what you'll have is a bunch of options. And if you click on this anthropogenic features, click there, so you see a bunch of dots. And what you can do is zoom in and click, and it'll tell you Apollo 11 reflector. So there's an object left by Apollo 11. So they landed right there. It's kind of cool. So if you come back out again, you can kind of pay attention to that when you look up at the moon. They landed somewhere right there, and that's kind of cool. So something else to notice also, put that away. We'll bring up nomenclature so you can learn some of the names of these features. Put that away now. And so here's Mare Imbrium, Mare Serenitatis, and Tranquillitatis, where Apollo 11 landed. And so there's lots of cool things you can see. And one thing I'd like to do is to actually, well, given the features, let's point out another cool feature is that you can look at geologic features and then click on these Mare age units. And not getting into too much detail about this, is basically what it's going to plot is these colors showing you the different ages of these units of lava flows. So the darker blues are the older flows, and then the lighter shades over here, there are younger, so they happen more recently. They're still many billions of years old, but this is a relative scale, so down to your right are areas where there are relatively old flows, and then the newer flows to your to your left. I'll turn that feature off so we can get back to what the moon looks like. And so you've noticed these dark spots. I mentioned that there are ancient lava flows, and you might wonder, why are they darker relative to the other areas? And part of that reason is the iron that's in the rock. So if you click on Kaguya, it's a Japanese mission that flew to the moon, and you click on FeO, iron oxide, and you'll notice these bright areas are where there's a lot of iron on the moon. And so that's part of the reason why that color distinction is there when you look at the moon. It's shades of gray, but the darker shades of gray are due to this iron abundance of these units. So again, this is the side of the moon that you do see from the Earth, but because we've flown spacecraft to the moon, you can now turn it around and see the other side of the moon, the side we don't see from the Earth. And something that should jump out right away is that there's a very big difference between the two sides, right? So let me keep flipping it back to the other side, the side we see from the Earth. We call it the near side of the moon. See the dark areas that are there, the ancient lava flows. But if you flip to the side we don't see from the Earth, we call it the far side of the moon. Not many. There's a few spots with the dark areas. So that's a neat, unique feature of the moon. Why there's this distinction between the two sides. It's an fairly open question. Still trying to figure it out. Last thing I want to show you with this feature, with this tool, is topography, or the surface elevations on the moon. And I'm going to use data from the Lunar Reconnaissance Orbiter and its altimeter. So LOLA, Lunar Orbiter Laser Altimeter. And if you click on that, what you'll see is just the surface elevations. And we'll start with the side we see from the Earth, the one that has the Maria. And the blue colors, the blue bright colors, are showing you areas that are relatively low. And the greens, the yellows, the reds are higher and higher elevations. And again, you see the side we don't see from the Earth being higher in elevation. There's this low area on the southern pole of the moon. This is a giant impact crater. It's huge. It's about 2,500 kilometers across. So it's a giant ancient feature on the moon, and clearly an impact crater. But again, going back to this idea that the two sides of the moon have a lot of differences that we try to figure out what that is. But anyway, it's a really cool tool. There's a lot of data that you can explore and kind of play with it yourself. So I'm going to talk more about the moon, but it's always nice to be able to interact with information yourself. Let's see. Now I'm going to switch back to my PowerPoint. So it's playing again?
Yeah.
Okay. So I'm going to go on. So something I want to talk about is how did the moon form? And we'll see in a second that also has to do with how the Earth formed, and because these two objects are linked. Here are two images of the Earth and the moon. The sizes are to scale. If you think of the moon, it's about 1/4 in diameter, and so you should be able to fit about 4 moons across the Earth. The distance is not to scale, it's much further apart than shown, but just to show you a comparison between the two. And we'll start asking the question of, how did the moon form? One of the oldest ideas of how the moon formed is this idea of fission that George Darwin came up with. He's the son of Charles Darwin. I think he wanted to get away from his dad's biology roots and decided to go into physics. And so the idea here was that back a long time ago, the Earth was very hot and it was spinning really fast. And it spun so fast that a little blob of it came off and flew off and formed a second object. And that was what the moon was. And that's the idea with this model. and it's called fission, so as the name implies. And people looked at the globe as well, looked at the Earth, and noticed that, hey, look, the Pacific Ocean is this huge area on the Earth that doesn't have any land. So they actually proposed, as you can see in this 1907 paper, they were talking about this idea, well, maybe there's all this missing continental mass, and that's probably what the moon was. So that was how they try to justify this model. There are some issues that people have had with this. Make this to work, the Earth has to be spinning really, really fast. One day being about 3 hours, so it takes 24 hours right now for the Earth to spin. But imagine it's much, much faster, and it's not clear if it was spinning that fast, and also how it got to that state in the first place. So another idea, and I'm showing you also the dates of these models, just to illustrate that it's relatively a new finding, right? So we were having this discussion about how the moon formed in the 1960s as the Apollo program was going on at the same time. So it's something that's 50 odd years old in terms of figuring this out. So here's another idea. It's called capture. And it's the idea that the moon formed somewhere else and came close to the Earth, and the Earth grabbed a hold of it, and then the moon went into orbit, and that's how the moon formed, essentially. One issue with this is that it's really difficult to make this happen. If you talk about the physics involved, you get the Earth, something the size or the mass of the moon, coming close to the Earth. Gravity doesn't work quite nicely that way. You have to do all these kind of exotic situations to make this to work, and it's not that obvious as I've shown in this cartoon. Another idea was co-accretion. The idea was just like in the early solar system. Here in this image on the left, I'm showing you kind of what the early solar system might have looked like, with the sun in the middle and this debris disk of dust and particles, and then the planets forming from that disk. So similarly, the idea with this co-accretion idea is that the Earth was in the middle and there was this debris of material close by, and that's where the moon came to be. It was essentially made out of the same stuff. And so one of the issues with this is that the Earth's density and the moon's density are somewhat different, right? So the Earth is about 5.5 grams per cubic centimeter. The moon is more like 3.3 or so. So there's a difference in density, and it's difficult to understand why that would be the case if it was made out of the same material. So that was one of the issues with this model. And so over time, this is the fourth idea, really, and I'm going to show you the quote standard giant impact model. There are others that have been proposed in the recent years and that have slightly modified this idea, but this is essentially what we're talking about in the sense of how the moon formed. And the idea here is that in the middle, the bigger object is the ancient Earth, and something the size of Mars approximately came and impacted. So here's a simulation by Miki Nawajima from University of Rochester, showing this impact process and doing the simulation to show after the impact, there's a lot of material that gets thrown into Earth orbit. A lot of it comes back to the Earth, and some of it stays in orbit, and that's how the moon formed, when some of these particles came together to form the moon. So I'm going to pause a bit I mentioned Apollo. We've been celebrating 50-year anniversaries of the Apollo program, and the next one is in a few days. That is Apollo 13, which launched on April 11th in 1970. And as many of you might know, it wasn't somewhat successful. There was a lot of issues with the mission. It's called a successful failure because of the problems that they faced. And as a side note, hopefully you can see me. This movie, Apollo 13, is how I got into all of this in the first place. When I was a kid, I saw this movie, and I wanted to be an astronaut, and then the moon and flying to space was kind of linked from an early age. So Apollo 13 has a special place in kind of my personal story. So I wanted to kind of mention that there's an upcoming 50th anniversary of this mission. I also want to show you where the different Apollo sites are. Obviously, these landers are cartoons and shown, much bigger than they actually are, just for in terms of scale. And I pointed out Apollo 11 already, and there was 12, 13, 14 landed close by to each other. Then you had 15, 16, and 17. So 6 missions that landed on the moon, and something that they did was they brought back samples from the moon. They brought back lunar rocks that people have looked at and analyzed to what it's made out of, and trying to figure that out. And I'm showing you one sample. So this is one rock, and so you'll see on the top it has a number 60015. So the 6 is for 16, Apollo 16. And so this is one sample. They've just cut this rock into different pieces. So you'll notice that the outside of this rock and the top left image is fairly dark gray color. But when you cut into it, it's dramatically different. It's a much brighter, lighter colored material. And that material is a mineral called plagioclase. And I've listed the chemical formula if you're interested. It has calcium and aluminum among the silicon and oxygen. But so this is a unique rock because most rocks are made out of multiple different types of minerals. So if you go outside, pick up a rock and you cut it open, you'll see there are lots of different types of minerals that this rock that you picked up is made out of. But this rock that they picked up from the moon is mostly just one mineral, and that's just one mineral that's composing the whole rock. So these findings of this type of rock led to this idea that the moon cooled in this kind of unique way. And it's generally called the lunar magma ocean. So I'll start with the left. And the idea is that the moon formed really, really hot. So it formed out of a giant impact, formed really, really hot, to the point where most of the moon was this giant ocean of magma, right? So if you've seen images of lava flows in Hawaii or things like that, you'll notice, so this is, imagine the entire moon like this in a giant ball of magma. And so as you imagine, if it's really, really hot, it cools over time. And what happened was initially as material cooled, the solids that formed were more dense than the liquid it's in, so that they sank to the bottom. So when you go from the left image to the one in the middle, what I'm trying to show you is that that solid material would grow from the bottom up as material sinking and becoming solid. And then something interesting happens. After about 80% of the way through, then that mineral that we talked about, that plagioclase, that mineral that made those rocks very bright colored, those start forming. And that mineral turns out to be less dense than the magma it's in. So what happens is that that mineral starts to float to the surface. And that's what I'm showing you in this middle diagram, that the moon starts forming this very early crust on the top, as well as, still forming the bottom. The blue material is still forming. So there's these 2 steps now. So there's the magma ocean now is sandwiched. It's getting smaller and smaller. And on the right is the kind of the mostly solid moon that we know of today. If you're interested, the time scales are interesting, like how long this process takes, going from the leftmost case where the moon just formed to kind of mostly being solid. It takes almost a blink of an eye in terms of geologic time. 10,000 years is very fast. And then you'll notice that going from the middle to the end case, when you just have 20% of the magma ocean remaining, it takes 10 or 100 million years. It takes dramatically more time. And that's because that crust that formed on the moon is basically like a blanket. It's putting a stop or limiting the amount of heat that's being released. So it just, it's forming and it's getting thicker also, right? So it's not just forming a lid of constant thickness, but it's growing as well. So it's making it more and more difficult to release heat through the surface over time. So that's why there's this dramatic change in how long these processes take. So overall, this process probably took tens or hundreds of millions of years, something like that. We're still trying to figure that out. There's some uncertainty there. And so here's an animation, probably a better way of showing this, that Yi Zheng developed, that shows you the steps. Initially, as we talked about, that those solids form and they sink, and once most of it has solidified, and then that's when some of that material, that plagioclase material, forms and then floats to the surface to form the crust of the moon. So part of what I do is trying to model this process using a computer. So take physics, how things cool, and then try to develop a Python code to go through this process. So if I want to show you what that looks like, if you're interested, let me see if I can switch to Chrome again. Okay. Perfect. And so some of you might be familiar with GitHub, and if you're interested in seeing what I kind of do on a day-to-day basis almost, is taking this story and trying to develop a code that'll run through the calculations. So if you're interested, it's just lines and lines of code that breaks this process up into smaller and smaller pieces, and then you try to incrementally figure out, okay, at this step, how much energy is being released, and at the next step, how much energy is, and then you try to sum up the time, and then try to figure out how long the moon took to cool. So if you're interested, that you can find the link there to see the steps involved and how to break this up into different lines of code.
Cool.
Go back to back here. So part of what I do is use very basic physics to build a Python code, for instance, but I also use codes that are much more complicated, that have been developed over decades. And this is an example of a code that people have been using for a while to model impacts. So here's, I'm gonna play you a clip. There's a lot of information here that you really don't need to worry about. Basically, it's plotting two different things on the two sides. Temperature is a simple concept. We can kind of watch that. And what you'll see is an impact happening, and this is modeling that process of how impact comes in, breaks apart the crust, and it kind of does something similar to what you'd expect if you threw a pebble into water, right? So there's sloshing and things like that. So it's a different type of code. So it's just a lot of things with computers and trying to figure it that way. So I'll go back to where we started with the formation of the moon, because I want to talk about kind of the big picture overview of what happened to the moon. And so we talked about the moon forming in this giant impact, with the early Earth getting hit by another body and producing a lot of material and putting into Earth orbit, and then the moon forming out of some of that debris, that material that's in orbit around the Earth. And this is an animation that NASA developed, which kind of shows you the steps afterwards, that what we think happened. So I talked about the moon forming in a very hot state, basically a ball of magma, and it cooled over time. And here is showing you that initial crust that the moon formed, and it just cooled very slowly. There are impacts that happened. I showed you that huge impact crater on the southern pole of the moon, South Pole Aitken Basin, and that is trying to show you that particular impact on this on the South Pole. Here are other impacts that happened later. These are, you won't recognize them right away, but hopefully in a moment you'll recognize what these are. And so many impacts happening to the moon early on. We're talking about 4 billion years ago, and a lot of impacts happening, punching through the moon. Those impacts would produce not only craters, but then it also produce their own lava flows that'll take their time to cool. And you should probably start recognizing the moon now as that lava has cooled, those dark areas or maria on the moon. And when it reorients itself, you'll recognize the rabbit on the moon, the man on the moon, whatever you see when you look up at the moon. So even after that, a lot of smaller impacts happen on the moon to modify the surface of the moon. And slowly it'll come to view of what we recognize today. So as kind of planetary physicist, what I try to do is figure out this process over billions of years. How did it start? How did the moon form? How did it evolve over time to get to what it is today? So that story we try to figure out by looking at data, looking at rocks from the moon, as well as developing computer codes to do that. So forward, pause here and take questions. I wanted to show you this picture that many of you may recognize. This is a famous picture from Apollo 8. It's called Earthrise. First time human beings saw the Earth with their own eyes, right? So this is incredible. There's images before with robots and spacecraft, but this is the first time there were human beings on a spacecraft in orbit around the moon, looking back and seeing the Earth. So I picked this picture because it's really cool. It's very famous, but also this was taken at the end of the year 1968, which, if you look up, was an incredibly difficult year worldwide, a lot of things going on. So I think given what's going on today, so I think this is a good kind of way to be hopeful and kind of look towards the future as you know, there's we need to get through a lot in the next couple of weeks and months. So so it's a cool picture I wanted to use, and so I'll stop and take questions.
Fantastic. Well, thank you so much for a really neat presentation, our most in-depth dive into the moon we've ever had here on Exploring by the Seat of Your Pants. Viranga, if you want to come out of screen share so we can see you again,
Sure.
I'm going to invite everyone who is tuning in on YouTube. If you guys want to type questions in the chat bar, I'll take as many as we can. But I want to start with a question. You showed us some Apollo moon rocks that were brought back. Have you ever had the chance to work with any Apollo moon rocks, or?
Yes, actually, when I was doing my graduate work at UC Santa Cruz, University of California, Santa Cruz, I had opportunity to work with a very small sample. I think it was Apollo 17, and we're doing some work with magnetism, trying to figure out how magnetic these rocks are. So yeah, I've had the opportunity to work with them a little bit, not too much, but yeah.
How many total rocks have been brought back from the moon? Like total amount, like in weight, or however you want to phrase it?
Good question. So the Apollo missions, I think the total is roughly 380 kilograms, I think. Also the former Soviet Union had 3 missions that landed and brought back samples, robotic missions. I think in the ballpark about 300 grams of the material. So they also had their own samples. So somewhere in there. So let's say 400 kilograms worth of material. Yeah.
So you showed a few pictures of Apollo missions. Apollo 13 is what inspired you. Obviously, this is a key turning point for you in your understanding and excitement about the moon. In addition, you mentioned 300 kilograms were brought back by astronauts, 300 grams brought back by these robotic missions. So other than the fact that we can just get more stuff, is there any added benefit to people going to the moon rather than robots going to the moon in terms of our ability to understand it?
So I'm not a geologist, but the geologist answer, I think, is yes, definitely. I think as a geologist, you're trained to see just your environment, your surroundings, the context of what happened far better than I think a robot can. That's obviously going to change with more technology, with development of artificial intelligence and things like that. it's not to say that robots don't have a place, right? So the computers, the robots, the spacecraft, they're going to do wonderful work. But I'm totally biased in the sense of saying we should go back. I think part of it is a human experience. It's not really a scientific thing. Sometimes it's where we humans connect when we see other humans doing certain things, right? So there's a human connection to that when you talk about going to the moon.
Fantastic. Listen, we get that all the time with astronomers, is that we can do all the science there, but without that connection, that draw, that Earthrise photo, which we had probes taking pictures like that, but it was just the fact that people were there doing it that made all the difference. So very cool. All right, we got a couple questions on YouTube. Our first is, when was the last impact on the moon?
So it depends on the size. There are very recent, maybe within the last couple years, if you look at the Lunar Reconnaissance Orbiter's camera, there's a website, which is lroc.asu.edu. They'll have these kind of images where they blink between a previous image that they took a few years ago and a more recent image, and you can see there's an impact that happened. A very tiny one, a small one. So the moon is still being impacted right now by smaller objects. But it's a good question of when. It depends on when was the largest, like what's the largest scale you want to look at. So
Right.
Something like Imbrium, you saw that giant circular feature on the moon. That's probably around about 4 billion years ago. So a long time ago. But yeah, you probably wouldn't have huge impacts anywhere under 1 billion years ago. So billions of years ago is when like the noticeable features would have formed.
Yeah, but I love this idea that it's always being impacted, and this is true of the Earth too. It's just that on the Earth, these meteorites disappear amidst other rocks, whereas on the moon, there's nothing to abrade them away. There's no atmosphere, so we get this permanent, beautiful record of all these impacts, which is amazing.
So yeah, there is some degradation from impact. So impacts, like if you form an impact crater of a certain size, other impacts of a smaller scale could degrade that crater or that feature over time. Also, there are thermal effects. So if the moon has this drastic changes in temperature when there's sunlight and when there's not, and it's a very dramatic change in temperature. So when a rock goes through variations of temperature, it becomes very hot, very cold, very hot, very cold. They put stress on it and it'll break. And the surface does change, but yes, you're right, much, much slowly than say the Earth when we have rain and we have wind and things like that. Yeah.
Very cool. I love that we ended up getting the question that you and I were discussing before we even went live. So Meg wants to know, what would happen if the moon never existed? I know this could be a long answer, but we'll keep it as
yeah. So that's a very interesting question. I think particularly with when we talk about biology, people have talked about, well, the moon produces tides on the Earth that kind of helps the sloshing of the oceans. Was that necessary for early biology? Certainly would have less of a tidal effect. The sun also has some influence on Earth's tides to a lesser degree. So if the moon never existed, we wouldn't have these dramatic tides that somewhat 2 times a day. And so there are interesting consequences also in terms of the Earth's spin axis. It's fairly stable. You want it to be fairly stable. You don't want it to be, flipping around. I think Mars may have had, I think people have done work on seeing how Mars is kind of the orientation Mars spins has dramatically changed over time. And that's perhaps not Mars not having a large moon. Mars has 2 small moons, very small compared to our moon. But maybe the moon has this kind of stabilizing effect on the Earth. So I think it's hard to answer that in a short span. I think it's a very complicated process, but yeah, I think there are lots of interesting consequences of the moon existing.
Super neat. All right, we're going to take a few more questions. So we got another one on YouTube. Is there any evidence of oxidation on the moon, or that there was oxygen ever on the moon?
Oxidation. That's a good question. No, I don't think so. Part of it is that when you look at rocks on the moon, you think of it being the opposite, where there isn't oxygen, right? So if you look at a rock, so we talked about iron oxide, for instance, right? So if there's a lot of oxygen, say like the Earth, then the rocks and the minerals that form would incorporate that oxygen, and then what you'd see is material that has more oxygen in it. The moon, on the other hand, has the opposite issue, where if you look at a rock, it does have oxygen, like iron oxide, we say, because oxygen is somewhat common. It's a common material in the solar system. So it's not that surprising you'd find it in the rocks, but yeah, to a much lesser degree than the Earth. Yeah.
Awesome. All right. Again, we could go all day with questions, but we're getting near the end. So what I want to do is, you highlighted this amazing LROC resource. You highlighted Apollo 13, which is an amazing movie and totally stands up. It's great for people today.
Right.
What other resources can we send people to learn more about the moon, about the missions there? Like, what are your favorite things that inspired you?
Oh, so this is how long is this? 3 hours long? There's a lot. There's a lot to do. I actually taught a course last semester at Johns Hopkins called Our Moon, and the whole course was on the moon. And it wasn't just about the science or the engineering; it was about the history, and it's about the religious aspects, the mythology, the music and movies, and all this stuff. And so you can find it ourmoon.space. It's the course website, and all that material is still there. I have lectures in PowerPoint format. I have YouTube videos there if you're interested. I have also links to other interesting resources. So if you want to know more about the engineering of the Apollo program, you can go in and kind of explore on your own. There's a lot. Movies wise, I think if you're interested in just the Apollo program, this is a good one, From the Earth to the Moon. It's a HBO series that they did in the mid 1990s, I think after Apollo 13. But very good. It's kind of a reenactment of everything that happened in the Apollo program. What else is good?
I'm just going to highlight Apollo 11 on Prime Video. Just came out fairly recently, and it's supposed to be one of the best. It is an amazing, amazing movie. So I encourage that to it. And From the Earth to the Moon was also a book called A Man on the Moon. So before it became a series, it was a great book.
Yeah,
just something to check out. Yeah,
there's a ton. I think just there's a lot of information on the internet. So I think yeah. Fantastic. Also contact me. I'm happy to answer questions and the various things. If you tell me, like, if you're interested in this aspect, I can try to find where to point you.
We've gone down the rabbit hole. Again, we could take 3 hours, but I passed along the link to your site. I passed along the link to VROC. So lots of cool things there. And yeah, Viranga, thank you so much for joining us today. We really appreciate you telling us the story. And yeah.
Cool. Thanks for having me.
For everyone on YouTube, do keep checking us out. Again, 100 sessions this month alone, featuring scientists, explorers, and more amazing stories. For now, have a wonderful rest of your day, everyone, and see you later.